Grade 12 learners, welcome to the Scienceless channel. Probably this is one of the most challenging weeks in your metric journey. There is an old saying that goes, the roughest road always leads to the top. Remember that this week. In today's video, we'll be looking at an exam prediction for Physical Sciences Paper 1, particularly the physics paper. I would like to give you just one advice on the instructions and information. Read these instructions before you step into the exam, days before you go to the exam, because these instructions are always the same, they never change. Do not spend a lot of time in the exam room reading this information while you have access to it prior to going to the exam. Question 1 of your exam will definitely be multiple choice questions. So you'll get 20 multiple choice questions, each giving you 2 marks. Right? So the multiple choice question will read as follows. Various options are provided as possible answers to the following questions. Each question has only one correct answer. Choose the answer and write only the letter A to D next to the question number. You will have 1.1 to 1.10 in the answer book. So here they've given us an example. So this example, they used K, even though we don't have K in our options, but they're just showing you that you only write the letter. Do not write the statements. Let's jump into our question 1. Question 1 says here, which one of the following statements is correct for the law below? So already they tell us that what they've given us here is a law. And then we are looking for the correct statement for this law. The law reads as follows. The net force acting on an object is the same as the rate of change of momentum. So we're saying here that the net force is equals to the time rate of change of momentum. This to me looks like Newton's second law, the momentum vision, right? So when I go to my options, I have to see Newton's second law. And in fact, that is A there. It cannot be the law of conservation of momentum. It cannot be universal law. It cannot be conservation of energy. It has got to do nothing with energy. So here when we answer our question, we will say we are on question 1.1. Then our answer is A. Question 1.2. An unknown planet orbits the sun as shown in the diagram below. The graph shows an inverse relationship between the force of gravity and the distance between the center of the two masses. So on this diagram here, we have the planet orbiting the sun. So you can see that the planet here, the direction of orbit, it goes in this direction, it moves like that, and comes there and orbit like that. So this is orbit of the unknown planet, is the path that the unknown planet actually follows when it orbits the sun. Now this graph shows a relationship, an inverse square relationship. Remember that this is a problem that uses the universal law of gravity. And we know that the force and the distance are inversely proportional, but they have an inverse square law, meaning you have to square or put a square root when you look at the relationship between the two when they change. So on this graph, they've given us the force of gravity versus the distance between the centers of the masses. Now they say here, what is the magnitude of the distance between the center of the sun and the unknown planet at point Y? So when this unknown planet gets to point Y, what is the distance there? We're looking for the distance R here. What is the distance here? right? Now, in order for, so they've given us a couple of options here that we'll have to look, we'll have to look or get. Now, in order for us to do this question, we will run through a series of equations so that we are able to break this question down. The first thing that I will do is that I will determine the force that we have using our universal law of gravity to say the universal constant times the mass of the sun times the mass of the unknown planet over the distance between the center squared will give me the force. Because I'm looking for the distance, I'll make it the subject of the formula. I'll cross multiply here, this will multiply that, right, giving me an r here squared, but also the f will multiply here, right, coming down there to give me the f like that, right? So I'll take the square root on both sides. So this would mean that my r will be the square root of the universal constant, mass of the sun, mass of the planet over f. So this is how we'll define r. Now, you have to note that this r here, we get it when we have the force f, the universal constant, the mass ms, and mass mp. That's where we get the distance r. I'll call this distance, I'll say r is given by a big R here. I'm using a big R because I can see on my graph that they're using that big R. So I'll say this small r is the same as the big R. But this occurs when the force is F, the mass is ms and mp, right? And of course we have the universal constant. Now, I want to come to a situation now where I look at the r when our planet is here at point x, right? So this is the r that occurs when the force is F16. So what do I mean? I mean that if I pull my equation, I'll say r, I'll call this r at x, right? Because it's the r at this point here. I'll say r at x is equals to the root of the universal constant ms mp all over, we have 16f now, because at x we have 16f, right? So this is this part of the graph, right? We want to see if we will get this 1 over 4r, right? Now, at this stage, I will take the one as a common factor and 16 as a common factor, so that now I have the universal constant mass of the sun, mass of the planet over f, right? Because if I multiply by 1 here, I'll get this. If I multiply by 16, I'll get that. Now here I'll use the rules of sets, right? From mathematics, we know that we can write this as the root of 1 over 16 times the root of GMSMP over F. Now, if you take the root of this, you can use your calculator, it should give you 1 over 4. But notice that this guy here is exactly this guy here, right? They're exactly the same, right? These are exactly the same. We said this is R, then I can write this as R. That's the reason why when we have a big force here, we have a small force of 1 over 4r, because they're inversely proportional. A big force would mean our objects are closer to each other. And you can see here that the sun is a bit closer to the planet in terms of distance. Now I'm going to do the same to try to then determine if the force is F2, what do we get at y, right? So this point here is point X. Now we want to see what do we get at point y when we have F2, meaning when we are here, right? So we'll do the same math here to say r at y will be given by the universal constant ms mp, but the distance, the force here now is F2, so that now I will have a common factor of 1 over 2, right, multiplied by g ms mp over f. I only have an f here because this times this will give me that, this times that will give me that. Now again, using our rules from mathematics of the sets, we'll have 1 over 2, we'll have here g ms mp over f. And again, you can see now that this will be 1 over the root 2, which here will have an r, because this guy here is exactly the same as this guy here. So now this tells us that when we are at this distance here, our r is going to be 1 over root 2 r. So this is the point here at y, and actually is what they were asking us to get. So our option should be B here, right? So our option will be B in this question, 1.2. So the answer is B. Now I'm going to stop here, but I want you to do the same method to see that if the force continues to decrease, because the force was decreasing here, hence the distance is increasing. If you can check here now, 1 over root 2r is bigger than 1 over 4. You can check that on your calculator. Now as we go down to get to 1 over 4 as our force, we get a much bigger distance, right? And you can see here the distance is getting bigger. You know, we had the smallest distance here, it was increasing, it's also increasing here. I want you to do the same math using 1 over 4f and see if you can get the 2r, right? Now let's go to question 1.3. Question 1.3 reads as follows. An object is thrown vertically upwards from the height h. After reaching the maximum position, it returns to the same height h. Ignore the effects of air friction. So here we have an object that moves from the height h as the initial height. So this is hi. And it goes up until the maximum point here. We know the v here will be 0. Then it comes back to the same height. So this height now is the final height where it ends its motion. Now the question says, which one of the following combinations is correct about the motion of the object? Now they've given us an option that says the work done by the gravitational force measured in joules, and the work done by the kinetic energy measured in joules. I'll firstly start looking at the work done by the gravitational force. Now to do that, we're going to say 1.3. Now the work done by the gravitational force is given by mg h initial minus h final. You need to know and memorize this formula. It's not in your information sheet. And in fact, this formula is the one that we use to define what a conservative force is. So this, according to this formula, we are going to say mg, the mass of the ball, times the acceleration due to gravity. I'll keep it as g for purposes of doing this question. And we discussed that the height initial will be h. So I'll substitute h here, and the height final, we said also it will be h, right? I'll substitute h here. Now this would mean that we'll have mg, h minus h is a 0, right? This means then that the work done by gravity is equals to 0 joules. And this is not surprising, because if you look at this type of motion, these objects move from point A and goes to point B. But point A and point B are the same height. So this is what we call a closed path. This is what we call a closed path, right? when you move from the same initial point and come back to the same initial point. And actually that's how we define the conservative force, to say the work done, and the conservative force is a force in which the work done in a closed path is zero, right? And we can see that the work done by this conservative force, and it's the only conservative force that we have, is equals to zero. So now on the options that we have here, we can see now that this one, is in the right path. The other ones cannot be. But we also have to check if this is true for us to choose C, right? Now, in terms of looking at the kinetic energy, we know that our initial velocity will be V at A, right? Let's say is equals to some number V. I'll choose a number V, right? It could be 2 meters per second or 3 meters per second, right? We also know that when this ball comes to the same height, right, it will have VB, but this velocity will actually be going in the negative direction. It will be the same in magnitude as the velocity that it goes up with, right, but opposite in direction, right? When this goes up positive, this one should be negative. We call this, when we did our projectile motion, vertical projectile motion, symmetry, right? We said the motion in VPM is symmetrical, right? Is symmetrical. The velocity that the speed that the object goes up with is the same as the speed that it goes down with, right? They're the same in magnitude, but the velocity is not the same because the directions are different. Remember, when you define velocity, you also have to attach direction to it. So only the magnitude is the same of the velocity. The speed is the same. So I'm going to use my equation for kinetic energy at A to say is given by K, A is equals to half mv A squared. But we said that our velocity is V, so I'm going to write that as V squared. So this is the velocity that we have when the object is at this point, right? I'm going to then calculate KB as well to say this is KB half mv B squared. Now remember that kinetic energy is a scalar quantity and we only substitute the speed here. So I'm not going to put the negative because the negative would mean we're calculating velocity. Even though when you put the negative it will cancel, but it is not correct to put the negative there because when you put the negative it means you're putting the velocity. But this thing here is not velocity, it's speed. You only put the magnitude. Now notice that these two are the same. The kinetic energy at A is exactly the same as the kinetic energy at B. They give me the same thing. It looks the same. Half mv squared, right? So this consolidates our answer to say this is also correct. So C will be the correct answer here. We'll keep this at C. Now we'll go and do question 1.4. Question 1.4 says that a tennis ball of mass M is dropped from a height h above the ground as shown in the diagram below. So there's an error here, typo, but anyway we can understand. Now in this diagram we can see that the ball is being dropped from this height that is measured from the ground, h, right? Now we know from vertical projectile motion that when we say something is dropped, it means its velocity is 0 meters per second. So I'm going to call this initial velocity because it's the velocity when it started moving. So this ball moves up until it gets to this point here. They say here ignore effects of air friction, and then further ask us to say which one of the following represents the change in momentum of the ball when it reaches height half h, right? So when it gets to this point here, what is the change in momentum? So the change in momentum is defined by m change in v, right? Perhaps maybe I could write this equation in this form. The change in v, maybe I can write it as final velocity minus initial velocity, right? We are looking for for this guy here. We are looking for this guy here. Now, we already know that the velocity here is 0, so no problem there. It means we need to find the final velocity here, right? Then we can then take this final velocity and substitute here in order for us to then determine our change in momentum. Now, there are various ways of doing this. I can see this as a vertical projectile motion problem, where I'm going to then use the equation that says final velocity squared is equals to initial velocity squared plus twice the acceleration and change in y. I want to also advise that you can say the mechanical energy Emec initial is the same as the mechanical energy Emec final, right? And this equation will expand into half mv initial squared plus mgh initial is equals to half mv final squared plus mgh final, right? Mgh final. This equation is also applicable in this problem because there's no air friction, meaning the mechanical energy is conserved. The mechanical energy here initially at the top is the same as the mechanical energy here at the bottom. You can use it then to also determine the final velocity here. You will get the same answer. In fact, I'm not going to use this method. I want you to try it on your own and see if we get the same answer. Now, from this, I will then say my final velocity squared is equals to 0 squared because the initial velocity is 0. Here we'll have 2g. And then our final height. Remember that our initial height, we started at this height here, which is h. Our initial height is h. Then this will be our final height. So our final height would be 1 over 2h minus the initial height of h. Right? Now, as we continue with this, we'll have final velocity squared is equals to, the 0 will fall out so that I have 2g. And we know that when we say half minus a 1, we should get a negative 1 over 2h, right? And I will then take the square root on both sides to say this is going to be the 2 and the 2 would cancel each other as I multiply here. The 2 and the 2 will cancel each other, and I'm only going to be left with a minus gh, right? That will be my final velocity. And remember, when you take a square root here, you can say plus or minus, right? But I won't do that because in this situation, I'm choosing down as positive, right? So that the velocity here, it comes out as positive. So I'm automatically taking the one that's positive. I'm avoiding to work with negative. You can also take the negative, it will give you the correct answer. Now, at this stage, we then employ our equation of change in momentum to say it's given by m v final minus v initial. Now, this gives us the m, and here we have negative gh minus a 0 here. Now, I'll stop a bit to check my options here to see where are we going. So I see that we have options that says half mv 2mu. So u, remember, is the gravitational potential energy, negative mv, and the root of negative mu. Okay, so at this stage, this thing simplifies to be something like m times the root of negative gh. Right? That's where we simply get to at this stage. Now, I can see from my options here that the v is not there. There's no way I can get a v in my equation. So they fall out. But there's something very interesting. How do we bring about the u, right? Now I can rewrite this equation, or rather m, as m squared, the root of m squared, if I could put it that way, because this is exactly the same as that, right? If you take the root of this, it will give you m, right? So that I multiply here by negative g times h. And we know from the rules of sets that if you have a times b, right, the root of a times the root of b will give you the root of a times b. The root of a times b. I'll do the same here to say I'm going to have m squared times the negative g h all over a square root, because I can take the square root of this alone and the square root of that alone to go back there, right? Now it's important to see that I can manipulate this so that I have the gravitational potential energy. I can write this as negative m. I'm taking the negative here and putting it in the front, right? And then I'm multiplying here by m, because m times m is m squared. So that I have mgh, right? And I still have the square root. Now I'll group these two, right? I think already you can see where I'm going, so that I have the root of negative m. This here is the gravitational potential energy, so I'm going to write that as m. So that means my change in momentum is the same as the root of negative m times the gravitational potential energy, the root of the product of the mass and the gravitational potential energy. And in fact, that comes out to be option D. So our answer here would be D. Please try this question using the conservation of mechanical energy and see if you get the same answer. We'll then now jump into question 5, 1.5. That says to us, the SI unit for power is, right? And I can see they've given me the kg meters per second, kg meters per second to the power negative 3, and so forth. Now, to answer this question, we'll use the formula of power to say power is defined as the rate at which energy is transferred, or the rate at which work is done. Now, I will further then break this to say work is given by force cos theta times change in x over change in t. Now, I'm taking this root because I can see that we have the kg meters per second, and I know that it will come from the F, right? Remember that you can simply say this is the same as joules, right, per second, right? You can take that root, but we don't have that option there. That's another unit of power, but we don't have that option on the options given here. That's why I'm expanding the equation. Now at this stage, I know that force is measured in kilogram meters per second squared, and this part here, it's like a ratio. It doesn't have SI units, right? It's a trig ratio, right? It will only give you a number, right? And so when we then put here the meter, we're going to have a meter, right? And time is measured in seconds. Now this would mean that I'll have the kilogram. Now the meter and the meter, I'll keep the base and add the exponents. 1 plus 1 should give me a 2. And I still have here to the power negative 2 divided by s. Now, when we continue with this question, we'll have kilogram meters per second. Now here I'll have per second squared. Remember that we have a division here. It means I'll keep the base, the s, and subtract the exponents. I'll have negative 1 here, right? Subtract the exponents. So that at the end of the day, I'll have kilogram meter squared per second to the power negative 3, because negative 2 and negative 1. So this is negative 1, not 11. Negative 1 should give me a negative 3. Now let's see if we have that option. Kilogram meters per second s to the power negative 3. We actually have that option as D. So the answer here would be D. 1.6, they say to us that an ambulance siren emits sound waves at a frequency of 700 per second, traveling at 30 meters per second towards an accident. Assume that the speed of sound is 330 meters per second. Now, what information do we have at this stage? I'll write down my given information. I'll say the frequency of the source, because the ambulance is the source, is the one that emits the sound waves. Now, you can see here it's measured in per second. We know that a hertz, or rather per second, is the same as a hertz, right? So I'll write this as hertz. And then we are all told that the velocity is equals to 30 meters per second. And then the speed of sound in the air is assumed to be 340 meters per second. Now the question goes on to say, what is the frequency, right, detected by a car moving behind the ambulance at the speed of 10 meters per second, right? So we are looking for the frequency of the listener, right, because it's the one who's going to detect the sound waves when they are moving at the velocity of 10 meters per second and they are behind the ambulance, right? They're moving towards the ambulance and the ambulance is moving away from the listener, right? This would be a question that requires us to use the equation of Doppler effect, where we're going to say we have plus or minus that all over plus or minus Vs. Now, we know that this is 700 here, this is 340. Because the listener is moving towards the source, right, we're going to put a positive here because we want to get a big number in the numerator, right, so that when we divide, we are able to detect a bigger frequency. Remember, when you divide a big number by a small value, you get a bigger frequency, right? Yeah, because our listener should detect a bigger frequency if they're going towards the source, right? And at the bottom here, we're going to have 340, and you must understand that the source is moving away from the listener, right? And when it moves away from the listener, what's going to happen is that we want to have a smaller frequency that will be detected if the source is moving away, right? For that to happen, it means we're going to put a plus here, right? The 30 meters per second. Why? Because if we put a plus here, we'll get a bigger value. And if you divide by a bigger value, you should get a small number here. You know, if you divide by a number that's getting bigger, if this number is getting bigger, because when you add, it's going to get bigger, right? That means dividing by a bigger number, you get a small value, and that small value will be the frequency that's detected. So in this question, we have a combination of the two, right? The listener going towards the source and the source moving away from the listener. We're going to get a value that's in between, right? So this is something that we can quickly do on our calculator to say we have 340, it's a plus 10 here, then we have a 340 again, and it's a plus 30, and we get an answer that says the frequency of the listener would be 226.16 hertz. Let's see if we have that option, right? 226.16, yes, that would be our answer. A would be our answer here. We then jump to question 1.7. Question 1.7 says that two spheres with charges 2q and negative 3q exert a force F on each other when the distance between their centers is r, right? So here we have the information that q1 is equals to 2q and q2 is equals to negative 3q, right? And we say we get the force F when this is the case, right? Also our r being equals to that r. right? The distance being equal to r. Obviously, this question you can see that it uses Coulomb's law. So how to define this force? We'll say F, the electrostatic force, the Coulomb's force is given by the Coulomb's constant Q1 times Q2 all over r squared. Now I'm going to substitute my values here that I have, so that I have K here, and here I have 2Q. Remember that when we substitute on this equation, we only take the magnitude of the charge, not its charge, whether it's positive or negatively charged, right? So I'm going to put 3Q here, and then our distance here we're saying it's r, the big R squared. Now when we simplify this, we can see that the 2 and the 3 will give me a 6. I'll have a 6, and then I'll have a K here, and this 2 will be Q squared, because I'm going to keep the base and add the exponents, and at the bottom I have R squared. And we're saying this gives us the force F. So if this is the case, if we have this charge and that distance, our force is F. That's what we've been told in this equation. Our force is F. Now they then come and say each charge is doubled, right? Each charge is doubled. Now our Q1 is now doubled. If we double this, we're going to say times 2 here is going to give us a 4. Sorry, that should be a 4Q, right? And Q2 is also doubled. If you multiply this by 2, it's going to be a 6. So we're going to have a negative 6Q, right? And they say also, and the distance is now 2r, so the distance is also doubled, right? So our new distance here is going to be 2r, right? Now the question says, what is the new electrostatic force? What is the new electrostatic force experienced by each charge? Then they've given us options here. You must be able to see that if you change this, right, and you change the distance as well, the force is expected to also change, because they're inversely proportional. They have an inverse square law as well, just like the universal law of gravity. So now to do this, we'll come and say the new force, I'm going to call it F prime, right, to denote the fact that it might not be the same as the previous force. So the F prime will be given by K, Coulomb's constant, Q1, Q2 all over r squared. This is our formula. Now I'm going to substitute what I have now. Here is K, we have 4Q, we have 6Q. Again, we don't put the negative there because we only take the magnitude. And then we're going to divide this by 2r squared. Now this will simplify to be the 4 and the 6 should give me a 24. So I'll have a 24K, and then the Q and the Q will be Q squared. And then here, obviously when we square the 2 is going to be a 4, and the r squared will be r squared. When you divide 24 by a 4, you should be able to get a 6. I think you can use a calculator at this stage. You should be able to get a 6, and then you'll have a Q, we'll have a KQ squared all over r squared, right? Now when I look at this guy here, he hasn't changed a bit. It's still the same as this guy, so we're still getting an F here, right? So this is equals to F. So what does this mean? This means our new force F prime is the same as the previous force F, right? So this means that these parameters have changed such that they still give us the same force, right? They've changed such that they still give us the same force as the previous situation. The distance is doubled, but the charges also have been increased so that they produce the same force. So on our options, we can see that this cannot be true, this cannot be true. But in fact, if one says to me that the force remains the same, right, the new force will remain the same, that will be a good option for me. That is 1.7. We're still getting a D. Now we jump to 1.8, which says to us that the electric circuit below has 2 bulbs, right? We can see the 2 bulbs here, A and B. connected in series. Now these two bulbs are in series with each other, right? And the switch is open. We have a switch open there. We can see that we have a power source here. It's a cell because we only have one of these here, right? Now the question further goes, so there's nothing happening here really. If you go to the ammeter here, there won't be any current that you read because the switch is open, you know. Remember that our current, we expect that it moves from a positive to negative and coming to this side. But you will see that when it gets to this point, the switch is open, then there won't be current. Current won't jump into this other side. All right. Now they say if the switch is closed and bulb B fails, so the switch is closed, bulb B fails, the reading on the ammeter will be, so what reading will we get here on the ammeter? What reading will we get here on the ammeter? Obviously the ammeter measures current, so what reading will we get there of current, right? Now as I was talking about this, you would realize that when we close the switch, again, this is the positive and the negative terminal. We expect our current to move from the positive to the negative. We expect current doesn't really move, but actually what moves is the charges, right? The amount of charge would move from the positive to the negative, and the movement of that charge we say is current, right? We choose positive to negative because we use conventional current. It's possible for current, in fact in reality the current moves from negative to positive, but we use conventional current where our charge, the charge flows from positive to negative. Now when our charge flow, it will flow from that point getting to this point. Now when we get to this point, the bulb fails. In other words, it doesn't allow the charges to flow coming to this side, right? It will stop the charges from flowing at this point. So from here going forth to that direction up to this point, there won't be current, right? The current will be zero because it's been stopped. 0 ampere is been stopped here. So here the current will be 0 amperes, right? And in fact, that is one of the disadvantages of a series connection, because in a series connection, the current doesn't divide. The current here should be the same as the current here. These two currents should be the same. So if the current fails to pass here, it will not get to this point in any other parts of the circuit, right? So our option here, the current can never increase, right? But 0 makes sense. The current can be 0. It cannot decrease because at this point it stops, right? This is not an option, right? So 1.7 is B. This is 1.8 actually. 1.8, our option is B. Now 1.9, it says here, which one of the following is correct for the statement below? They say here, an electrical machine that converts mechanical energy into electrical energy. You know, some of these things, before you look at the options, try to answer them. We expect our answer here to be a generator, because we all know that the generator converts mechanical energy into electrical energy, right? We know that from our understanding of motors and generators. Now, if we look at our options, it cannot be a motor, right? It cannot be a capacitor, it cannot be an inductor as well. Now, B is very interesting. What they're doing at B is that they're trying to be specific, in a sense that we have two types of generators, right? We have a DC generator, we have a DC gen, we also have what we call an AC generator. An AC generator. And the AC generator is called an alternator, right? It's called an alternator, right? So this one converts alternating current. It converts mechanical energy into alternating current, into when you say current, it will be an electrical energy, right? And a DC current simply converts mechanical energy into a direct current, right? So our answer here is the alternator, So the answer here would be B. 1.9 would be B. Then we jump into 1.10. 1.10 says an atomic hydrogen from a distant unknown galaxy emits radiation and it is recorded using the spectrometer on Earth. The emission line spectrum A shows the recorded frequency of the atomic hydrogen. After a decade, the absorption spectrum B detects a pattern of dark lines on the visible spectrum of the same galaxy. So let's break this question down. So we have a distant galaxy that has hydrogen atom in it, or hydrogen atoms in it. Then we use a spectrometer on Earth as a device that will detect the type of light that we receive from, other objects, like in this case, the galaxy, right? Now, we then have an emission spectrum on A that shows us what has been detected from this distant galaxy. Now, before we go to that absorption spectrum, the emission spectrum I meant to say, I just want to look a bit at the visible spectrum here because it will help us to answer this question. The visible spectrum basically shows the rainbow colors: your violet, indigo, blue, yellow, green, yellow, orange, and red. And we know that the colors that are from this side, they have a longer wavelength. They have a shorter wavelength. So I'm just going to use the less than sign there to say they have a shorter wavelength. And this means here they'll have a higher frequency. They'll have a bigger frequency, right? And the more we move towards the red side, the wavelength actually starts increasing, it becomes longer. So that then this side we have a bigger wavelength, right? And when we have a bigger wavelength, we know that the frequency should be small, right? Should be a lower frequency. Now, this relationship is defined by this equation that says velocity is equals to frequency times wavelength, right? This is a formula for a wave, right? Or light or sound, because those are wave. And we can see from this formula that the frequency is inversely proportional to the wavelength. That's why when we have a shorter wavelength here, we have a high frequency, right? And here we have a longer wavelength, then we have a lower frequency because they're inversely proportional. So the colors, as we go towards this direction, these colors increase in wavelength and decrease in the frequency. Now, using that information, let's look at the emission spectrum. Our spectrometer detects that the hydrogen is made up of the violet color, the indigo color, the blue color, and the green color. Remember that the absorption spectrum appears black, right? All of it appears black. Then it starts showing colors when it detects a certain type of light. It then shows those colors. So it means this appears as violet, this appears as indigo, this will appear as blue, and this will appear as green. All right? So this is what we detect when we did our spectrometer from Earth. Now, after 10 years, a decade later, we run the same experiment, right? But in this case, we use the absorption spectrum, right? The absorption spectrum is exactly the opposite of emission spectrum. It shows the visible colors, right? So it shows all these colors: the violet, indigo, blue, green, orange, and red, right? But when it detects a certain type of light, it absorbs that light and shows it as a dark line, there, as dark bands, right? So now from the same galaxy, we detect now violet, blue, green, and red, right? Because it's an absorption spectrum, they appear as dark lines now instead of the visible colors as we had in emission spectrum. Now, when we compare these two, we can see here that what used to be violet, right? At the far end, it is still now violet, right? After 10 years. But it has moved a little bit. Do you see that now? It has moved a little bit. It moved somewhere to this point, right? Somewhere to this point. And what used to be indigo, right, is now blue. So the indigo has moved again towards the blue color, right? It has moved towards the blue color. And what used to be the green, right, has now moved. What used to be the blue has now moved towards the green side, is now green, right? And what used to be actually green has moved towards red, is now red after 10 years, right? So we can see that the same hydrogen from the galaxy, right, now gives us a violet, blue, green, and red, right? So what's happening here? What's happening is that our light that we're detecting from the hydrogen or from the distant galaxy has moved towards a longer wavelength and lower frequency, right? It has moved towards the red side of the spectrum. And in fact, this is what we call a red shift. This is what we call a red shift, right? So this phenomenon tells us that, as time goes on, the galaxies or the objects that are in a distance from us are actually giving us more of red colors. They're moving towards the red side. Now, let's see what they ask us in our question, because we have analyzed the situation and I think we are pretty much ready to answer any question that comes our way. They say here, which one of the following combinations is correct about the wavelength of light? So which one is correct about the wavelength of light from the galaxy and the distance from Earth to the galaxy? So two things. What can we say about the wavelength? Well, definitely we know that the wavelength has moved towards the red side of the spectrum, right? So has moved, or it's moving towards a shorter wavelength, right? Because we're moving towards shorter wavelength, colors that have a shorter wavelength, right? So our answers should be here on shorter wavelength. Now these two are out, right? You cannot consider them. Now what can we say about the distance from Earth to the galaxy? Now how do you come about the distance? Remember that if you study Doppler effect, we will tell you that if you have a high frequency, right, it means the source is going towards the listener, or the listener is going towards the source, right? They're getting closer to each other. The same is true when we study light. If, let's say, for example, you have a bulb here, right, and you are closer to the bulb, the frequency would be big because the wavelength here, your lambda, is short, right? So here we have a short, or rather a shorter wavelength. So we expect the frequency to be higher. Now, if you were to have a bulb this side and you are far from this bulb, the light will take time to reach you. So the wavelength is longer, right? The wavelength is longer, and then we expect the frequency to be smaller, right? We have a decreased frequency, right? So this is to say, when you are closer to light, that's why you see the light becomes bright, it shines on you. But when you are far, it becomes faint. You don't have a lot of luminosity, we call it, right? So our options between these two, we expect to have a decreased frequency because our wavelength has been increased, right? Our answer should be D, right?